The title of my talk is Monitoring Fish Behavior in Challenging Environments, Special Considerations of Tracking Fish with Acoustic Tags. I'm going to talk about acoustic noise and its impact on sampling. Then I will talk about how tags can be detected in noise, and then show some examples of studies that were completed in noisy environments. So the problem with acoustic noise in acoustic studies is that sometimes noise can be misclassified as data. So I'm going to talk about how this can be avoided. The sampling environment can have a big impact on the implementation and outcome of an acoustic tagging study. We have established that acoustic tag technology can be used, for example, in a forebay upstream of a dam or in open water areas in both freshwater and marine environments. Tagging studies and bypass evaluations conducted at hydroelectric projects and elsewhere for over the last decade have shown that. But now we want to sample in areas like a tailrace where there's lots of noise. What makes this environment bad for acoustic tag studies? Well, I think we all know the answer to that. It's noise. Noise comes from several sources. It is entrained air or the bubbles in it, density differences that cause changes in the speed of sound, junk in the water that blocks the sound direct path, electromagnetic interference, noise from motors and generators, and other acoustic systems. We know there is noise, but how does it affect the data? And then, once you have determined the source, what can you do about it? So we can observe this noise in the data, which I will show you in a minute. But next is a little review. My background is in hydroacoustics, and it turns out that many of the things I know from hydroacoustics is useful for acoustic tagging studies. Understanding about transmit pulse widths and ping rates and receiver gains gave me a good start for doing acoustic tagging studies. Those of you familiar with fish finders, hydroacoustic surveys will recognize on the left is an echogram from a mobile survey. For the echogram, time is on the horizontal axis, range from the transducer is on the vertical axis. The blue dots are echoes from fish in the water column, and the yellow line indicates the reflection from the bottom. So from this echogram, the graphical interface on the right for the acoustic tag system was built. The developers of this tagging system admit that they were walking the path of least resistance when they built this system, using a lot of what already worked from the hydroacoustic system. So for a short review, a hydroacoustic transducer converts electricity to sound, transmits a short pulse of sound at regular intervals, listening in between those transmissions for sound that is reflected or echoes. The acoustic tagging system used that framework, but moved the transmitter from the transducer into the tag in a swimming fish. Now the transducer is a hydrophone, just listening, but now not listening for reflected sounds, not echoes, but for direct pass signals from the tag. So on the right, we have a similar output for acoustic tags. Time is on the horizontal axis, but rather than range on the vertical, we have tag code. For this example, it is tag code 5512.00, indicated in the upper left corner. Here. This is the interval between tag transmissions, 5.512 seconds between transmissions. So the tag code is like the pulse rate in hydroacoustic systems, transmitting at the exact interval programmed for the tag. Because of the fact that this tag transmits with this exact interval every time, it makes a repeatable pattern, as do all the tags programmed to transmit at different intervals. By adjusting the vertical scale to the exact time interval, it makes the pattern a horizontal line. Other tags are observed as diagonal lines. This is the tag code, the timing between transmissions. Instead of a name, it has a repeatable pattern. It's like how you know who is coming down the stairs by the cadence of their step. It is another way of knowing. So this timing method of tag detection has several benefits, including its influence on the range of tag identification, being able to differentiate tag returns from noise, and being able to differentiate direct path tag returns from reflected returns, called multipath. So now I can show you what noise looks like. Here's an acoustic tag system graphical/visual interface showing entrained air as the vertical diffuse blue lines throughout. Note that the double blue lines circled in yellow is the pattern that indicates a tag is present. The tag code indicated in the upper left corner is 3660.738 here. Also note that the graphical interface can be used to adjust the receiver gains up or down, just like a hydroacoustic system. The scale on the right is voltage, and you will want to make sure that the returns from the tags are not too high on the voltage scale, not too pink. This is an example showing ADCP noise. It's diffuse with intermediate voltage in the yellow zone and pulsing as indicated by the blue spikes here on the bottom left. This is an example of what electrical noise looks like in the visual interface. Note, there are no tags present here. The graph in the lower left indicates the pulse interval rate of the noise, which can sometimes be used to track down its source. So the message here is we can see noise and we can see tags. This visual interface provides a tool for identifying tags in noisy environments. But what if the noise is constant, like entrained air in a tailrace, not isolated intervals as shown here? What can you do? So here's something that those familiar with hydroacoustics will recognize. This is a screen capture from an oscilloscope. Time is on the horizontal axis, voltage is on the vertical axis. We're just looking at the turquoise signal now. We will talk about the gold line in a minute. The big turquoise signal, bracketed by the vertical lines, is the transmit pulse. It is equivalent to 1 division, which in this case is 2 milliseconds. This can be the pulse width selected and programmed in the tag for sampling, or this can be the pulse width selected and programmed for sampling. This is a 5 millisecond pulse width. If the previous slide was an example of saying, hey, this is analogous to saying, hey. So to recap, we can monitor in noisy environments because we can use the graphical interface to see the noise, to differentiate it from the tags, and increase or decrease the receiver gain. And we can adjust the pulse width to provide ample opportunity for the tag to be heard within the sampling environment. Here's another example of noisy data. The tag is shown on the left in the graphical interface. You see the tag and lots of other tags and noise. On the right is a georeference map of hydrophone locations that really has nothing to do with what I'm talking about, but it's a great map of a location that shall remain nameless. So what else can we do with tags in noisy data? The answer is software. Filtering allows removal of noise to isolate the tag. So we can monitor in noisy environments because we can use the graphical interface to see the noise. We can use the graphical interface to adjust the receiver gain. We can adjust the pulse width, increasing the time the tag transmits, and we can filter in software. So remember this screen capture from the oscilloscope from a few minutes ago. This is the transmit pulse in turquoise. It is called CW, short for continuous wave. The gold line is what the turquoise signal looks like once it has been received, and it's called the detected signal. There are several electronic gee-whiz processes and filters that go into making this detected output. None that are really that interesting. But there is one process called matched filtering that turns this CW pulse, wide peak, Christmas tree looking thing, into this narrower output pulse, which results in a much smaller variance in the signal arrival time and reduces the effect of noise. So we can monitor in noisy environments because we can use the graphical interface to see the noise. We can use the graphical interface to adjust the receiver gain. We can adjust the pulse width, increasing the time the tag transmits. We can use filtering in software, and we can use matched filters. The result of minimizing error and isolating the tags from noise allows tag transmissions to be received with very high accuracy by several hydrophones. In much the same way a GPS works, by knowing the positions of the hydrophones and accurately measuring the signal arrival time at each hydrophone, it is possible to estimate the locations of the tagged fish using this equation to triangulate a position in X, Y, and Z, using the time of arrival from 4 different hydrophones. This is called triangulation. This is not drawing a line from time of detection on hydrophone 1 to time of detection on hydrophone 2. Here is an example of triangulation of a tagged fish as it moved through an array of 6 hydrophones. Each position, or red dot, is estimated by the time of arrival at 4 different hydrophones. Now I'm going to show you some examples of studies in noisy environments. This system 2D tracked tags in a highly aerated portion of the tailrace. These green, yellow, and blue dots are 2D tracks of tags that were dragged behind a zodiac from the previous slide. These results were obtained by using a wide pulse width, increasing how long the tag transmits. These acoustic tag results include only returns that could be resolved into 2D tracks. By that I mean those that were detected on at least 3 hydrophones. These triangulated positions are resolved for locations both within the area defined by the hydrophone array, indicated by the 4 black dots, and outside of it. This system 3D tracked tags in the high flow environment of a turbine intake of a dam. The large blue, yellow, and red dots indicate the hydrophone locations. The red track indicates the 3D track of the tag that was positioned in the turbine intake. These results were obtained by using a wide pulse width, increasing how long the tag transmits, and the matched filter discussed previously. These tag results include only returns that could be resolved into 3D tracks, those that were detected on at least 4 hydrophones. This system 2D track tags in the noisy environment of an electric barrier. The visual interface on the right shows the raw data collection with the electrical interference indicated by the blue bands. The tag return is circled in yellow in both screen captures. The visual interface capture on the left shows the result of software filtering. To summarize, there is currently much effort in testing deterrent systems and the impact of anthropogenic structures on fish and other aquatic organisms. Often these deterrent systems alter the sampling environment and make the use of tried and true tools ineffective. But by using a system that can adapt to these altered environments, behavior modifications can be monitored. Thank you. Any questions?